Hello, my name's Alex, and welcome to Alex the Pi Guy. Today we're looking at the grade 9 academic course, and we're looking at the first section of that curriculum, lesson 2, which will be on exponent rules. The first rule we're going to look at is the multiplication of two bases, all to the power of an exponent, is simply the multiplication of the first base to the exponent by the second base to the exponent. If we write it out with our algebra, we can see our two bases here are multiplied, and then we apply the exponent to the whole thing. And that is the same as writing each base to that exponent and then multiplying the result. As an example, I have 3 times 2. All of that squared is 3 squared by 2 squared. And we can verify this by evaluating each side independently. So 3 by 2 to the power of 2 is 6, if we evaluate the base on the inside, to the power of 2, which by our definition of an exponent is 6 by 6, which is 36. If we evaluate the right side, we have 3 squared by 2 squared, that's 3 by 3, multiplied by 2 by 2, which is 9 times 4, which is 36. Our second rule is, if we have a base to an exponent multiplied by the same base to a potentially different exponent, is the same as that base to the power of the sum of the two exponents. If we use our algebra, that's like writing a to the power of b multiplied by a to the power of c is equal to a to the power of b plus c. Here we have an example. That would be 3 squared plus 3 to the 5th is equal to 3 to the power of 2 plus 5. If we verify our example, we'll need our calculator for this one. 3 squared times 3 to the 5 is 3 by 3 multiplied by 3 by 3 by 3 by 3 by 3, which is 9 by 243, which if we plug it into our calculator is 2,187. 3 to the power of 2 plus 5, on the other hand, is 3 to the 7, which is a lot of 3's. And if you plug that into a calculator, you get 2,187, which we should expect. The third and last rule we'll cover for this video is similar to the second rule. If we have a base and we put it to an exponent, and then we divide that by the same base to a potentially different exponent, then that's the same as writing that base to the power of the first exponent minus the second exponent. So here you have a to the power of b divided by a to the power of c. That's the same as a to the power of b minus c. So you just got to remember that the exponent on the bottom is being subtracted. I also made a note here that a can't be 0 because we don't want to be dividing by 0. In this example, I have 5 to the power of 9 divided by 5 to the power of 2 is equal to 5 to the power of 9 minus 2. And if we verify this result, 5 to the 9 divided by 5 to the 2 is a lot of 5's divided by 2 5's. If we plug this into our calculator, we get a very big number divided by 25, which is equal to 78,125. On the other hand, 5 to the power of 9 minus 2 is 5 to the 7, which is 7 5's multiplied together, which is 78,125, which is the same result, which is what we would expect. That's it for this lesson. Following this, there will be an aside on proofs, and I will then show a proof for each of the rules. It's not necessary for you to know these proofs or understand proofs, but if you're interested where these rules come from, then I encourage you to stick around. If you're not sticking around, thank you for watching. If you like this content, maybe drop it a like. If you want to see more of this stuff, maybe drop a subscribe. Let me know in the comments what you liked, what you didn't like, what you'd like to see more of. If the setup is working out for you, if you can read everything all right. Thank you for watching, and I'll see you next time. And now for the aside on proofs. I'm going to start with some notation, which I'm going to use for indexing. So if we have a to the power of b, that's a with a subscript of 1 times a subscript 2, and so on. These numbers don't mean anything in the math. It just is a way of keeping track of, how many a's I have, where along in this multiplication I am. Furthermore, we can do one for addition, where c times b is b to the subscript of 1 plus b subscript 2, and so on. Again, this is just used for notating where in this addition I am. It can be used for rearranging and things like that. And now on to the first proof. We have a and b are real numbers. And remember, we're only working with exponents that are natural numbers for now. And if we start on the left-hand side of that first rule, then we have ab to the power of c, and we expand it using the definition. Now I'm going to make a note here, and we're going to talk about this at a later point in the series, but multiplication is commutative, which means a times b is the same as b times a. This basically means if we have a string of multiplications, we can rearrange it however we want. It's still the same thing, which is a very, very handy thing for proofs, as well as other things. So with that in mind, we can rearrange all of these a's and all of these b's, such that all the a's are on the left and all the b's are on the right. So first we kind of drop these brackets, we expand this indexing into each of the a's and b's. So we have a1, b1 times a2, b2, and so on all the way up to ac, bc. And then we can rearrange them. So we have all the a's first and all the b's second. So the a1, a2 all the way to ac, multiplied by b1, b2 all the way to bc. And that simply is from the definition again. This first bit is just a to the power of c, and the second bit is just b to the power of c. And thus we have shown that ab to the power of c is the same as a to the power of c times b to the power of c. This little guy here indicates the end of a proof. Sometimes he's colored in completely to be completely dark. Honestly, I don't really know what it's called. My professors always just called it a tombstone, to say you killed that proof, because that's how exciting math is. Now the important thing here is that we didn't come up with anything new. All we did is we started with the first part of the rule, we applied the definition, did some math, and by applying that definition again, we got to that second part of the rule. That's a general way to solve proofs where you just use the definition to generate new information. There are other ways to solve proofs, but this is by far the simplest and the easiest one. And if you are expected to do any sort of proof, this is probably the method that you're expected to use. On to the second proof. For the rule where a to the power of b times a to the power of c is equal to a to the sum of b and c. So now if we let a be a real number, b and c be a natural number, then a to the power of b times a to the power of c, we use our definition to expand those two exponents. So a1 through ab times a1 prime through ac prime. We're using a prime here so we don't mix up the ones here and the ones here and the twos here and the twos here. Now I'm going to use an index shift. So all I'm going to say is that anytime I have a 1 prime, I'm going to change it to b plus 1. Anytime I have a 2 prime, I'm going to change it to a b plus 2, and so on. If I have a c prime, I'm going to change it to a b plus c. This doesn't change anything. All I'm doing is using indices to differentiate the different a's here. So this doesn't change how many a's I have. This is just a different way of labeling them. If we do this, then we have a to the power of b times a to the power of c is a1 all the way to ab. But now we're multiplying by a to the b plus 1 all the way to a to the b plus c. Now this part here is unnecessary information. We don't need to say that. We can drop that and just say it's a1 times a2 all the way to ab plus c. Using our definition again, that is just a to the power of b plus c. Thus, a to the power of b times a to the power of c is equal to a to the power of b plus c. End of proof. On to our third proof. So in this case, we have a to the power of b divided by a to the power of c being equal to a to the power of b minus c. Again, I'm stating that a is not 0 so that we don't have to divide by 0. So in our setup, we let a be a real number, such that a is not 0, b and c be natural numbers, and I'm going to use that b is greater than c because we want to make sure that b minus c is also a natural number. In the next lesson, we're going to drop that restriction, but for now, we're just going to look at b being greater than c. In the case where we have it where b is not greater than c, the proof isn't much different. So if we start at a to the power of b divided by a to the power of c, we use our definition to expand those two powers. We have a1 times a2 all the way to AB divided by A1 times A2 all the way to A to the C. Now since B is greater than C, which is a natural number, so it is greater than or equal to 1, we know that C lies somewhere between 1 and B, so we can add this little bit in the middle, where we have A1, A2 all the way to AC times AC plus 1 times AC plus 2 all the way to A to the B. Dividing again, we have our denominator is unchanged, being A1, A2 all the way to AC. And if we use our division, we can actually cut these guys out. All of this goes away, and we're just left with what's on the right here, which is A of the C plus 1, AC plus 2, all the way to AB. Now we're going to use our index shift, where last time we added B, this time we are subtracting C. So C plus 1 is now going to be index shifted to 1, so we've removed C from that index. C plus 2 is now going to be 2. All the way, if we got B, we're going to B subtract C. I want to note here that this triple equal sign here is just a definition sign. It's not an actual equal sign. So if we continue A to the power of B divided by A to the power of C, then if we use this index shift, then we're going to be left with A1, A2, all the way to A, B minus C. And that, by our definition, is just A to the power of B minus C. Thus, A to the B divided by A to the C is equal to A to the power of B minus C. And that's the end of the proof, and that is the last proof of this lesson. If you guys like this, aside, let me know. This is a little beyond the scope of what you would do in high school. You don't really do a lot of proofs, but personally, I don't think this is terribly hard. This introduces a lot of using algebra, which is maybe a lot at grade 9, but I don't think it's anything that you are incapable of. So anyways, if you like this video, again, maybe drop a like, subscribe if you want to see some more, let me know what you like, let me know what you didn't like, let me know what you'd like to see more of, and I will see you in the next one.